Hello, today we'll be covering lesson 6.4, rational exponents. You guys will be able to simplify expressions with rational exponents. Now, rational exponents just means that there is a fraction in the exponent. So we saw at the beginning of this chapter, if you have a fraction in the exponent, I like to say power over root to keep it straight in my brain, what goes where. And you can switch this back into a radical form, just like this. So to simplify, I'm going to suggest usually putting it back into radical form, like so. So this first problem, we are going to simplify with rational exponents. You'll notice we have a fraction in our exponent, so we have power over root. You know your root goes in front of your radical, your base number goes under, and then the power of 1 doesn't really change anything, so you can either write it or leave it out. Now, this is back in radical form, but it is not simplified. We need to check to see if we have any groups of 3 that we can pull out. So you'll notice 216 is reducible by 6 and 36. 36 is prime 6 and 6. So we have the cubed root of 6 times 6 times 6. Notice that is one group of 3. So this cubed root of 216 is actually a perfect cube. And we have our simplification is just 6. Okay? Now the next one, there is 2 ways to do this. I am going to show you both ways, and you can choose. So the first way that I'm going to show you is that if you recall, we can actually, if we have the same bases here, just add our exponents. So 1/2 plus 1/2 is actually just 7 to the first power, which is just 7. So the same base of 7, add the exponents, we are good to go, we get our solution. The other way is to do it how we just did above. We take the square root of 7 times the square root of 7. Switch them both back into radicals, and then the square root of 7 times the square root of 7 is the square root of 49, which is just equal to 7. So we wrote this part above the remember from section 6.1. A to the 1 over n power is the nth root of a to the first power, or just a. And a to the m over n power is the nth root of a to the m, or you can write this the nth root of a all to the m, like so. So we are going to work on these next 4 problems. We're either going to convert between exponent to radical or radical back to exponent. So we have first one, x to the 3/7 power. Remember, we have power over root, so we have the 7th root of x to the 3rd. Notice how we cannot simplify this any further because you cannot get 7 in a group here. So that is as simple as it gets, or you could write it the 7th root of x all to the 3rd power. Either is equivalent and correct. The next one, we have y to the negative 3.5 power. Now, what we want to do is actually put this into a fraction form. So I'm going to do that over here. We're going to write we want to write 3.5, which actually equals 7 over 2 as a fraction. If you don't remember how to do this though, 0.5 you should know is a fraction of a half. And then we have the multiply and add rule, where you take the denominator times the big number, so 2 times 3, and then add the numerator to that, and we get 7 over 2. Now I purposely left off this negative because that can get confusing there, but this is actually equal to y to the negative 7 over 2 power. Now we could go ahead and continue to simplify. So this negative in our exponent means this term is unhappy where it is. It wants to be not in the numerator, but rather in the denominator. So I now have 1 over y to the 7 over 2 power. Then I go ahead and do my power over root. So I have the square root of y to the 7th power. Now this can simplify. If we write out 7y's, and then we group them into groups of 2, we have 3 groups that come out. And we end up having y cubed with a square root of y left. So we'll write that in here. Still equivalent, still simplifying. Now, if you recall, we cannot have a radical in the denominator, so the first thing we had to remember here was the fact that a negative made it switch down. Now we have to recall that we cannot have a root in the denominator. So we are going to fix that by rationalizing. Now all we have to do is multiply both the numerator and the denominator by the exponent, or the radical part. So square root of y times square root of y is y, so we are left with root y over y cubed times y, which simplifies to square root of y over y to the 4th power. And then we are done there. So that was a longer problem. It's actually not too hard because there's only one variable. You just have to be willing to stick with the problem and try to figure it out. I would say the next 2 examples are a little easier, switching back to exponent form versus radical form. Remember, if there isn't a number out front, it's a square, so we once again have power over root. So we have the power 5 over the root 2. And that's basically the answer. You could also write it like this. Either way is totally acceptable. You can choose. I would probably choose this one, but you can choose the other one too. And then we have also the 5th root of b cubed. Now we have power over root. Once again, this root could the power could actually go inside, or it can stay outside. Either's fine. So we have b to the 1/5 power to the power, the 3rd power, because we have power 1 over 5 times this cubed on the outside. And then you can just multiply that through, so b to the 3 over 5 power is our solution. These are also technically equivalent to each other, so you could write them either way as well. All right, and then the next page. If you recall, when we multiplied and divided radicals, we had to have that our indexes matched. In these 2 cases, our indexes don't match, but we can actually solve them, believe it or not. So even though the indexes are different, because what is under the variable under each of them, or the number under each of them, is the same, we can solve. So what I am going to do is switch these to their exponent form. So I have power over root, so 3/4, and I have 2/8. Because of that, I switched them into exponent form. And then I can go ahead and recall that as long as my bases are the same, I can actually subtract the exponents to solve. I don't actually need to do any dividing unless there's big numbers out front of each of them. Now here's where it gets tricky and why our indexes had to match before. Because we have to find common denominators. So as long as you know how to find common denominators, you're good to go. So there's two ways you can go about this. We have 3/4 minus 2/8. You can see that this fraction could be reduced. You could get 3/4 minus 1/4, finish it out that way. Or if you didn't happen to see that, you could multiply this first fraction by 2 in the numerator and the denominator to then make the common denominator of 8. You'll notice either way you solve, you end up getting a half, okay? So I don't care which way you solve, choose the one that makes the most sense to you. I end up getting x to the 1/2 power either way. And then if I rewrite that as a radical, that is just the square root of x as my solution. Because we have our power over our root here. And multiplication works similarly. I'm going to go ahead and put these in exponent form. I have 3 to the 1/2 power based on this one times 3 to the 1/4 power. Now the bases of 3 match again, which means I can just add my exponents. So 3 to the 1/2 plus 1/4 power. Notice I have to get common denominators again. So I am going to try to get common denominators of 4, which means I need to multiply this first fraction by 2 in the numerator and denominator. So I get 2 over 4 plus 1 over 4 equals 3 over 4. So I have 3 to the 3/4 power. And then I can go ahead and say that that is equivalent to the 4th root of 3 to the 3rd power. And because 3 is actually a number, we can go ahead and take 3 times 3 times 3. And I get the 4th root of 27. I know that is not reducible any further because I will only have 3 groups of 3 as my primes. There is no groups of 4. And then lastly, we are going to simplify numbers with rational expressions. So I first start out by making this guy a fraction. So I have 2.5. I multiply and I add. So this is going to be 5 over 2. Don't forget this negative though. I leave him off on purpose when I'm doing this step, but I have to remember him later. So I have 16 to the negative 5 over 2 power. This makes the whole thing go into the denominator, so we have 1 over 16 to the 5 over 2 power. Then I have power over root. So I have the square root of 16 to the 5th power. So I'm going to just use a calculator and figure out what 16 to the 5th power is. That is actually a really large number. The square root of 1,048,576. Now, we could go ahead and do factor trees for all of this. That would take a very long time. So before you start doing that, I would try to find the square root to see if it happens to be a perfect square. And lucky for us, that large number is actually a perfect square. You can take 1,024 multiplied by itself twice and get the number. So we are done. 1 over 1,024 is your solution for this rational expression, simplified. We can do the same thing with part B. So we have negative 32 to the 4/5 power. Notice it does make a difference that the parentheses are where they are. If it was like this, that would mean something different, okay? That means you do this and then there's a negative tacked on to the front. With the negative inside the parentheses with the 32, you know it all goes together. So you have the 5th root of negative 32 to the 4th. Now the same reason why it matters to have parentheses here, if you plug this into a calculator, sometimes our calculators are silly, and if you don't put it in parentheses, it thinks, oh, negative 1 times 32 to the 4th. It takes 32 to the 4th, finds out what that is, and then multiplies it by negative 1. But you know, if you take negative 32 times negative 32 times negative 32 times negative 32, that has to equal a positive number, not a negative number. So be very careful when plugging into a calculator and make sure it doesn't do some silly things for you, okay? Anyway, when you take negative 32 to the 4th power, you actually end up happening to get the same big number we got the last time. 1,048,576. It just happened to come out that way. And then you can use your calculator to check for a 5th root, or you can do a factor tree and look for groups of 5 and find the answer. Either way you do it, you are going to find that this is actually a perfect 5th root and the solution is 16. 16 is our answer here, and we are good to go for today. Have a great day.